So in quantum mechanics, there's several big foundational ideas that the whole thing is built on. One of the big ones is that waves and particles are not really different things. Classically, we tend to think of waves and particles as two different types of moving phenomena. You've got a wave, which is basically a disturbance that propagates outwards, even though the individual particles are hardly moving. So we've got wave motion and particle motion as different things. Like if you've got a sound wave, you've just got the air oscillating and the oscillations travel, but the air itself hardly travels at all. Versus like wind would be the individual air particles moving a long distance. So that would be particle motion. And the main difference between those mathematically is what we're measuring. In both cases, you've got something moving, but for particle motion, the particle has momentum. Classically, mass times velocity. It's moving in some speed. It has a mass. Multiply those together, you get momentum. And for wave motion, a wave has a wavelength. So you can calculate the wavelength based on, actually, how would you usually calculate wavelength? If you have a bunch of other information about a wave, what could you use to calculate the wavelength?
Volume over frequency.
Yeah, or velocity over frequency.
Yeah.
The speed of the wave divided by the frequency. Or instead of writing divided by frequency, you could write times time. So they are kind of similar in some ways. Both the wave and the particle have a speed, and wavelength and momentum are both quantities you can calculate using the speed of the motion times some other quantity. Mass if you want to calculate momentum, or speed times period if you want to calculate wavelength. And they seem like completely different quantities on the surface. The things we typically treat as waves and the things we typically treat as particles do not overlap. Like you would treat sound as a wave. You would never treat sound as like some particle moving through space. You would treat a thrown rock as a particle. You would never treat the rock as a wave. But in the quantum approach, and they both have velocity because they're both phenomena in motion. In the quantum approach, we say that they're basically the same thing, or just two different ways of looking at the same thing. Every moving phenomenon can act as both a wave and a particle. We say it acts as a wave in the sense that it has a wavelength. We say that it counts as a particle in the sense that it has a momentum. And they're related by this idea of the de Broglie equation. That relates the wavelength and momentum. And anyone remember what that equation is, or have you seen that yet?
Is it the HC over wavelength one?
That's related, but that's really more about energy of light specifically. The equation is more about how wavelength and momentum are related to each other.
Okay. Is it the H over P?
One way to write it is that wavelength is Planck's constant over momentum, or alternatively that momentum is Planck's constant over wavelength. Or you could just multiply both sides by P or multiply both sides by lambda and say momentum times wavelength equals Planck's constant. So in this equation, P is the momentum. Lambda is the wavelength. And H is Planck's constant, which is a universal constant that happens to be an extremely small number. But the idea is that if you have something that you would usually treat as a wave, in the sense that it has a wavelength. If you take Planck's constant divided by that wavelength, you can calculate a momentum. And you could say the wave acts like a particle with that momentum. Or alternatively, if you have something you would usually treat as a particle because it has a momentum, you would divide Planck's constant divided by that momentum and get a wavelength and say this particle acts like a wave with that wavelength. The thing is though, if we're talking about an everyday object, like let's say you throw a baseball, the baseball has a momentum that's, let's say it's maybe approximately 1 kilogram, rounding off heavily, and you throw it at about 10 meters per second. Its momentum would be 10 kilogram meters per second, mass times velocity. But Planck's constant is so ludicrously small that if you, it's, I think something like 10 to the negative 19. Anyone remember the value of that? If you happen to have that handy.
It says
Negative 34.
Negative 34, oh, I was way off. So something times 10 to the negative 34, and I think is that joule meters?
Joules per second, joule second.
Oh, joule seconds, right. Thank you. So some absurdly small number of joules times seconds. So if you take something times 10 to the negative 34 and divide by, let's say, 10 kilogram meters per second, you still get about 10 to the negative 34, or let's say 10 to the negative 35, because we bumped it down a level. So the wavelength would be absurdly small. That's like smaller than the size of an atom. So if you throw a rock, you could hypothetically treat that as a wave. But its wavelength would be so nonsensically small that it doesn't make any sense to do so. There's no reason to treat it as a wave. Likewise, for a typical wave, like let's say we're looking at a sound wave, maybe its wavelength is 1 meter or 2 meters or something. Planck's constant divided by the wavelength of sound, maybe a couple of meters, that's going to be such a nonsensically small momentum that we could say, yes, technically the sound wave has momentum, but it's such a small number, there's no reason to even consider it as anything other than zero. So this doesn't really tell us much useful about everyday sized objects. Everyday sized particles either have lots of momentum and almost no wavelength, or lots of wavelength and almost no momentum. So everyday situations we can usually categorize as these things are waves, these things are particles, and they don't overlap. But if we're looking at the extremely small scale, like individual atoms, subatomic particles like electrons, protons, and light, the numbers are small enough that, for instance, Planck's constant divided by the teeny tiny momentum of an electron is a wavelength that's reasonably sized compared to the size of the electron itself. So for an electron, we have to treat it as having momentum and wavelength. We have to treat it as both a particle and a wave at the same time. Likewise for light. Light tends to have extremely small wavelength, like on the order of a few hundred nanometers maybe. Planck's constant divided by a few hundred nanometers is a momentum that cannot be ignored when we're talking about something on the size of an atom. So light acts as both a wave and a particle. It has a wavelength, its oscillations in the electromagnetic field, which we'll get to later, but it also comes in these discrete packets called photons that have their own individual momentum. Any questions on that so far? So the big upshot of all this, as far as we're concerned, is that electrons specifically act as waves as well as particles. And if you've got an electron in an atom, let's say you've got the classical view of an atom as, let's say, just a hydrogen atom for simplicity. You've got a proton, you've got an electron orbiting around. And the electron just whizzes around the electron like planets in orbit around the sun. But that classical approach doesn't actually hold up to physical measurements. The quantum approach is that the electron isn't a single particle. The electron is more of a wave confined to the region around the proton. And if you've got a wave confined to a small space, what happens when you've got a wave in a confined region? Like if you've got a wave on a string, but the string is tied off on both ends, or if you play a note in a room that's enclosed rather than just out in the open, what happens to that wave in a confined space?
It turns into a standing wave?
Exactly. So if we treat the electron as a wave, but it's confined to a finite region of space, instead of getting a particle in orbit, we end up with a standing wave. Kind of tough to draw that, but a standing wave in a ring, or more accurately, a shell around the proton. And yeah, we get oscillations. These standing wave acts as oscillations. This isn't really a very accurate picture, but the general idea that the electron forms a standing wave in the region around the nucleus. And those standing waves, if we look at it in one dimension, we get standing waves that look kind of like this. If you look at a two-dimensional standing wave, like let's say you take a drum skin and vibrate the drum skin just by striking it, the standing waves you get on the drum skin form a more complicated pattern of peaks and troughs in 2 dimensions, or nodes and antinodes in 2 dimensions. But in 3 dimensions, if you look at the standing wave in 3 dimensions, they form these distinct shapes that you might recognize as the electron orbital shells. All the electron shell shapes you see in chemistry, the reason for those shapes is because those are the shapes that form standing waves in 3 dimensions. So that's what the electron is. The electron is not a particle in orbit. The electron is a probability cloud that forms standing waves. And the behavior of the standing waves of the electron is why the atom behaves in the way it does. Any questions on that so far? And one of the most important things about a standing wave, can a standing wave just have any wavelength at all?
No.
No, there are only specific values, right? When we were looking at the different shapes of standing waves last time, we found that there's certain wavelengths that work. In the case of the one-dimensional standing wave, just all whole number multiples of a certain value. And anything in between doesn't work. You only get standing waves at these specific values, and the in-between values do not work. And it turns out that that's the same for the standing wave in the atom. You treat the electron as a standing wave, it can only have certain specific wavelengths, and therefore can only have certain specific momentum. The in-between momentum values don't work. You can also convert that momentum into an energy, which means that because it's a standing wave, it can only have certain specific values of energy. Any in-between values of energy don't form standing waves, and therefore they don't happen. So this is what we mean when we say energy is quantized. Quantized just means it occurs only in specific values and not in between. And that's also known as discrete. So discrete or quantized just means it only shows up in specific values and the in-between values don't work, as opposed to continuous, which means it can have all the in-between values as well. And so typically in everyday life, we tend to think of energy as continuous. Like you can have this much energy or anywhere in between. But on the atomic level, you can have this much energy or this much energy, and the in-between values do not work because they don't allow the electron to form standing waves. Any questions on the theory behind that so far? So if the atom can only have certain specific energy values, and we usually show that on a diagram by just having a list of the energies, sort of on an energy axis. Like let's say we've got an energy axis, and we don't have another axis, it's just essentially a one-dimensional graph. And maybe this is the lowest energy the atom can have. We might call that E sub 1 or sometimes E sub 0, depending on the scale. And maybe this is the next highest energy it can have. And it can also have this much energy, but the in-between values don't work. In that case, let's say you currently have an atom in the n equals 1 state. Let's say right now the atom is in energy level E2. If you want this atom to gain energy, how do you give extra energy to the atom?
By observing a photon?
Yeah, you shoot a photon at it, a photon just being a little blob of light. So you shine light on the atom, or more reasonably, you've got a whole cloud of atoms. Maybe you've got this chamber full of these atoms in the n=2 energy state. You shine light on them, that light hits the atoms, and either it can absorb the photon of light or it can't. Absorbing the photon would mean it bumping up to the next energy level. And this difference would be delta E. And it doesn't have to be the next energy level. You could jump up several levels at once. Maybe you go from E2 to E4 or E2 to E5. But you can't end up somewhere in between. A photon can't bump you halfway to the next energy level. Either it bumps you up to the next energy level or it doesn't. But this delta energy of the atom is provided by the photon. So the way we can write this as an equation is that the change in energy of the atom, or whatever quantum system we're talking about, the change in energy of the system equals the energy provided by one photon. And you can't really combine photons together. Either one photon has the right amount of energy or it doesn't. So this is very similar to the conservation of energy stuff we were seeing back in 7A as well. The classical approach in 7A would be delta E for the system equals, in 7A we were saying energy of the system was changed by what? What were the transfers of energy we were working with? Like if you were just writing out a conservation of energy equation way back in 7A, you start by, well, the types of energy could be potential, kinetic, thermal energy stuff, but what about the transfers? What would be the processes that change the total energy?
Is it Q plus W?
Yeah, the heat and work. Heat and work are the processes that cause the total energy of the system to change, because these are transfers of energy from somewhere else to the system or from the system to somewhere else. And so we have essentially the same setup here. For the quantum approach, we're saying delta energy of the system, usually just one atom or something like that, equals the energy of the one photon. The photon is acting as the process or the transfer that gives extra energy to the system or takes energy away. The photon is basically serving the same role that heat and work did in the 7A situation. Same idea, we've got a change in energy of the system equals the process that's giving it energy or taking it away. So if you're absorbing a photon, the absorbed photon becomes the change in energy of the system. Or if you're emitting a photon, the photon that's emitted is the energy that's lost. So formally, we should have a plus or minus here. Plus versus minus, depending on whether we're absorbing a photon to gain energy or emitting a photon to lose energy. Because if you were losing energy, let's say you go from E2 to E1, this would be the lost energy. And the atom loses energy by emitting a photon. If it drops down to a lower energy level, the excess energy is emitted as a photon leaving the system. And that photon, in a very real sense, is the lost energy. And then that photon might be absorbed by another atom somewhere else, or it might leave the system entirely. But the lost energy becomes an emitted photon, or if you absorb a photon, that becomes the extra energy you gain. And again, it doesn't have to be to the next level directly down. You could drop, for instance, from E3 down to E2, down all the way to E1. So you could lose this much energy and spit out a certain photon, or lose this much energy and spit out a certain photon. And as long as you're starting and ending at permitted energy levels. Any questions on that so far? So, and if it helps, you might draw it out like, if you think of this in terms of initial versus final. Let's say initial is, you've got a low energy atom and a photon heading towards it. And then the final state would be a high energy atom, or at least higher. And no photon at all. The photon has been absorbed. The photon has become the extra energy that the atom now has. Or that could also go in reverse. You could start with a high energy atom and end with a low energy atom and a photon leaving it. But the photon makes up that difference in energy. Any questions on that so far? Okay, let's put some actual equations into this. One of the big ones that you're going to be using in any such situation is the formula for the energy of a photon. Each photon has a very specific amount of energy, and it's very predictable. The energy of one photon depends only on what quantity. What property of the light determines how much energy each photon has? What are the properties of light that you think would make a difference here? Like if you got several beams of light, what could be different about them?
Wavelength?
Yeah, the wavelength is really the main difference we're going to look at. There's also to some extent amplitude, but amplitude, the brightness of the light, doesn't really tell you how much energy each photon has. Brightness is really more about how many photons, or more accurately, how many photons per second. The energy of one photon depends only on the wavelength, or alternatively on the frequency. You could write it either way. One way of writing this is energy is proportional to frequency, specifically Planck's constant times frequency. So wavelength or light with a higher frequency is going to have more energy packed into each photon. And again, the brightness of the light really depends on how many photons per second, as well as this. But the frequency is basically telling you how the energy is split up. High frequency light means lots of energy in each photon. Low frequency light means not very much energy in each photon. Or another way you could write that, how else could you write frequency? If we want to write this in terms of wavelength instead, how are frequency and wavelength related?
With velocity?
Yeah, velocity equals frequency times wavelength. So we can solve for frequency just by dividing by wavelength. Frequency equals velocity over wavelength. So we could rewrite frequency as speed over wavelength and get h times speed over wavelength. Planck's constant times the speed of the wave divided by the wavelength. However, since it's light, what would we use for v here?
C?
Yeah, c, the speed of light.
Casey, I have a quick question.
Mm-hmm.
What's the difference between this equation and the equation with the momentum times wavelength equals h again?
They're describing different quantities. The de Broglie equation is talking about how wavelength and momentum are related. So you could say momentum, for instance, equals Planck's constant divided by wavelength. And so this is largely for translating between momentum and wavelength. If you've got something that you know, if you've got a phenomenon where you know the wavelength, but you also want to treat it as a particle, you can calculate the momentum. Or alternatively, if you know the momentum, but you also want to treat it as a wave, you can calculate the wavelength. So the de Broglie equation allows you to translate back and forth between treating something as a particle by talking about its momentum, or treating something as a wave by talking about its wavelength. The equation for the energy of a photon, on the other hand, this isn't talking so much about momentum. This is talking about how to find the energy of one particle of light if you know its frequency and or its wavelength. So very, very similar in structure in some ways. They're both proportional in terms of the Planck's constant. But this formula is about finding how much energy one photon of light has, one packet of light. Whereas this one's talking about treating the wave as a particle or the particle as a wave.
Okay, thank you.
And energy is going to be more useful here because we're talking about the energy levels that the atom has. So if we want to deal with conservation of energy on the atomic scale, this one is going to be more useful. Or either one of these, really. But we usually describe light in terms of its wavelength rather than in terms of its frequency. They're equivalent equations, but this one often tends to be more useful. In fact, if we take a look at the light spectrum, if we look at visible light, let's say we go from, let's say blue to red. And then a whole rainbow of colors in between. The blue end of the spectrum is very short wavelength, high frequency. The red end of the spectrum is very long wavelength, but small frequency. So blue light has a very short wavelength and lots of cycles per second. Red wavelength is a longer wavelength, but fewer cycles per second. And then you've got all the colors of visible light in between. And then beyond that, you've got violet. Well, I guess this should really be the violet end of the spectrum. Violet and blue. Beyond that, you've got ultraviolet and gamma rays, X-rays, various other forms of light that aren't visible. Then beyond red, you've got infrared. And then beyond that, you've also got even longer wavelength forms of light like radio and microwaves. Actually, I think microwaves is on this side, which is why it's called micro. But if we look at this in terms of energy, if blue-violet light has a short wavelength, what does that tell you about its energy per photon?
It's increased.
Yeah, we're going to have a very large energy per photon. A smaller denominator means a larger result. So the energy per photon of blue-violet light is very high. Lots of energy per photon. Whereas for red light, we've got a long wavelength. HC divided by a long wavelength is going to be a smaller result. So we've got only a little energy per photon. And again, that doesn't mean that violet light is always brighter than red light. The brightness is really more dependent on how many photons per second the light bulb is emitting. But the energy per photon is talking about how energy is split up. One photon of blue-violet light has lots of energy. One photon of red light has very little energy. But you might have lots of photons of one and very few photons of the other. But this is very useful in terms of figuring out whether a color of light based on the wavelength can be absorbed or emitted by an atom by comparing the energy levels. If you know how much energy it takes to jump it from E1 to E2, you can say, well, a photon would have to have that much energy. Convert that energy to a wavelength, and you can then figure out what color of light is going to get absorbed by that atom. Or alternatively, if you've got high energy atoms and they're dropping to a lower energy level, you can calculate how much energy are they losing, and you would say that one emitted photon would have that much energy. Convert that energy to a wavelength, and you now know what color of light is shining outwards from the atoms as they cool off. Because that's how the atoms lose energy. They emit light. They glow. Any questions on that so far? So let's try actually running some numbers. One equation we can use, and so far the HC over lambda or HF, these work for any quantum system, because this is talking about the very nature of light itself. But the equations you would use to determine those energy levels we just looked at, those equations are going to vary from situation to situation. One common situation is the hydrogen-like atom. And by a hydrogen-like atom in this context would basically mean a fairly small nucleus with one electron orbiting it. So for hydrogen, an actual single proton, a single electron, this works perfectly. For other small atoms with one electron, or small ions, I should say, with one electron, it's going to be a pretty close approximation. But it should work perfectly for hydrogen. The idea is the energy in the nth state is going to be negative some constant, which turns out to be 13.6 electron volts, times z squared, where z is the atomic number, over n squared, where n can be any whole number, any positive integer. And electron volts is just a unit of measurement, specifically a unit of energy measurement. Specifically electron, this E means the charge of one electron. And it should be an absolute value because we don't care about the negative on the sign. And then V is volts. That just means joules per coulomb. Charge of the electron is, I think it's something times 10 to the negative 19 coulombs. Multiply that by joules per coulomb and the coulombs cancel out, so you get joules. So electron volts is just a very, very small unit of energy, a very, very small number of joules. And it's useful as describing energy at the very small level because it's based on the charge of an electron. But this is just a constant of proportionality. The important thing is that the energy of the atom, or rather the energy of the electron in the atom, is proportional to the atomic number squared, but that's going to be a constant, and inversely proportional to n squared, where n is a whole number. So there's many possible energy levels. Let's try calculating a few of them. And let's specifically assume we're looking at hydrogen. So Z equals 1, because hydrogen is number 1 on the periodic table. So if we start making some calculations, E sub 1, because again, n can be any positive whole number. If you plug in 1, you should get the lowest possible energy level. We know Z is 1, and we're plugging in 1 for n, so what would we get here?
Negative 13.6.
Yeah. Negative 13.6, and the units would be electron volts. And there's nothing really special about 13.6 as a number. It's just it's essentially the conversion factor that gives us the right units of measurement. And what if we plug in 2 for n? So we get 13.6 times 1 divided by 2 squared. What would we get there?
Negative 3.4.
Sounds good. So that would be the next energy level it can have. And note that this is a larger amount of energy because negative 3.4 is larger than negative 13.6. In fact, we could even graph these. If we just chart out an energy axis, and hypothetically, if we're dividing by larger and larger and larger numbers, what's the highest we could go if you divide by a really huge number? Like if you take negative 13.6 divided by 1,000,000 squared, or negative 13.6 divided by 10 trillion squared, that's going to get closer and closer to what?
0.
0. So 0 is the hypothetical maximum here. This equation cannot give you a result of 0 or higher. It's always going to be a negative number. But as n gets larger, this is going to get closer and closer to 0. So 0 electron volts is the top of the scale. In fact, much like the bond energy we were looking at way back in 7a, if you add enough energy to bring the electron to more than 0, you've actually broken the bond. You've given the electron enough energy to escape the atom and just drift off into wherever. So 0 is basically the limit for the electron still being bonded. If you bring the energy above 0, you've broken the bond, the electron escapes. But the negative 13.6 is the lowest energy you can have. So at the lowest possible level, we've got negative 13.6. For that. So negative 13.6, that's the n equals 1 state. Or we would say the first harmonic or the first quantum state. Because remember, this is still talking about a standing wave. The electron in the atom forms a standing wave. The first harmonic is this much energy. The second harmonic would be at negative 3.4 as the energy level. That's a fourth of the way up towards 0, right? Because we divided by 4. So halfway, fourth of the way, somewhere around here. So that's n equals 2 at negative 3.4 electron volts. And let's calculate E3 and E4 as well. So try that out on your own. E3, E4, and let's go with E5 also. Try punching that into a calculator if you have one handy. 13.6 divided by 3 squared, or by 4 squared, or by 5 squared. See what you get.
Three squared is negative 1.5.
Okay, negative 1.5, thank you. That looks like a little more than halfway up. So something like there. So there's n equals 3. Anyone have some values for 4 and 5 yet?
4 is negative 0.85.
Okay. And anyone have one for 5 yet?
0.54.
So for 4, we're at 0.5. And then negative 0.5. What do you notice about these energy levels as we go further up?
Smaller.
Yeah, these gaps are getting smaller. The energy levels are getting closer and closer together. And that essentially represents how easy it is to go from level to level. If you're at n equals 1 and you want to jump up to n equals 2, you need a huge amount of energy to get there. If you're at n equals 2, jumping to n equals 3 is somewhat easier. It's a smaller gap, a smaller amount of energy required. If you're at, let's say, 4 and you want to go to 5, that's much easier. And then these levels just keep getting closer and closer together as we go higher and higher up. Because we've got to fit infinitely many of them between negative 13.6 and 0. So the gaps just keep getting closer and closer together because we're approaching 0 as an asymptote. But with a diagram like this, it becomes much easier to tell the differences in energy. For example, let's say we are currently at the n equals 3 level, and we want to know what photons can be emitted. Or let's actually say the n equals 2 level. You're at n equals 2, and we shine light on the atom. And we want to know, can the light be absorbed or not? So to check that, let's say we start at n equals 2. If you're at n equals 2, so you're in the second harmonic of the atom, and you absorb light, what energy could you go to? You're absorbing energy, you've got to end at what sort of energy level? Or what are some possibilities there?
N equals 3?
Yeah, you could absorb, if you absorb exactly enough energy, you could jump up to n equals 3. Or if you absorb a little more energy, maybe you jump from n equals 2 up to n equals 4. Or if you absorb a little more energy, maybe you jump from 2 all the way up to 5. Or from 2 to 6 or 2 to 7, depending on how much energy you get. But those are the only possibilities. You can't go anywhere in between. You can't gain enough to go from like 2 partway up to 3. If a photon is carrying enough energy to take you from 2 only partway up to 3, the atom cannot absorb that photon at all. Or if the photon has enough to take it from 2 up to like halfway between 3 and 4, the atom can't go up to here and then drop back down to 3 and give change. It has to start and end at permitted energy levels. No other options available. So if we wanted to figure out what wavelengths actually work, what we can do is look at those differences. Like let's say we're going from 2 to 3. If we go from 2 to 3, how would we calculate the delta energy of the atom?
Would it be negative 1.5 plus 3.4?
Yeah, because we could just subtract final minus initial. So effectively, that's going to be E3 minus E2. So negative 1.5 minus negative 3.4. And you could use this equation for that. You could just plug in 3 for n, plug in 2 for n, and then subtract the results. But if you're going to be doing this several times, I usually find it much faster and easier and just more sensible to draw out a diagram like this, listing several energy levels, and then you don't need the equation at all after that. You can just take a look at the values you've already calculated. So this sort of chart is a very useful tool for streamlining the process. You just do all the calculations with this equation all at once, and then you don't need the equation anymore after that. So we subtract those, that's negative 1.5 plus 3.4, so I think that's 1.9, is that it? So positive 1.9 electron volts. And what could provide that energy to the atom?
Light?
Yeah, we've got to shine light on it. And since light comes in these discrete packets called photons, the change in energy of the atom has to equal the energy of exactly one photon. Because if one photon has exactly that much energy, then it's going to get absorbed and bump the atom up to the next level. If the photon has less than that, then it doesn't work. It can't put it partly up to the next level. So what we can do is we can set energy of one photon equal to 1.9 electron volts. And what's our formula for energy of one photon in general?
H times F.
Yeah. Or if we want to know the wavelength, I would write that as hc over lambda. And if we want to find the wavelength, we could just multiply by lambda, divide by energy. And we can use this combined with the energy of one photon we just found to determine what wavelength of light will make this work. So we could plug in the value of Planck's constant and the value of the speed of light. But since h times c shows up together so often in this formula, it's usually just described as its own constant. H times c is usually just standardized as writing it as 1240, and the units for that would be electron volts times nanometers. That's an energy times a distance. But usually, instead of writing it as joules times meters, we write it as electron volts times nanometers, because electron volts cancels out nicely with this electron volts, and nanometers is going to work nicely with the fact that wavelength of light is usually written in nanometers. So if we fill that in for HC, and then we fill in the energy of one photon that we just found, we can divide those, 1240 divided by 1.9, and we get about 653. Electron volts cancel out, so we're left with nanometers. So if you shine light that contains 653 nanometer wavelength, then some of those photons are going to get absorbed by the hydrogen gas and bump it up to the next level. And note that 653 nanometers is a visible wavelength of light. This is a color that you can actually see. I'm not sure exactly which color it is, but it's somewhere in the visible spectrum, somewhere in the, I don't know, probably greenish or orangish. So if you shine light of that color, it's going to hit the hydrogen and just stop. The photons get absorbed, which means they don't pass through. So the hydrogen gas would be opaque to that light rather than transparent. Light that gets absorbed does not pass through. Light that cannot get absorbed just passes through without any interaction at all. So some wavelengths of light, some colors get blocked by the hydrogen gas because they get absorbed. Other colors that cannot get absorbed pass through and the hydrogen is translucent to those. So you can check that for each one of these. If you take a look at how much energy this is from 2 to 4, you can convert that energy into a wavelength. The energy gap from 2 to 5, you can translate that into a wavelength. And you get a collection of specific colors that get absorbed by the hydrogen gas. And that collection of colors, that collection of wavelengths would be called the absorption spectrum. Spectrum in the sense of a variety of different colors. And that's usually drawn as the color bar, like from red to violet, with certain lines drawn in between to represent exactly which wavelengths are the ones that get blocked. Or for the emission spectrum, certain lines to represent which wavelengths actually leave the gas as it cools down. So that's where we get the idea of an absorption spectrum and an emission spectrum. Absorption spectrum is all the wavelengths of light that can be absorbed by the gas to make it warm up. Emission spectrum is all the wavelengths of light that can be leaving the gas as it cools down. Any questions on that? All right, then I think that's it for today. Try the other examples here, going from 2 to 4, 2 to 5, and even some emissions. Try going from 4 down to 3, 4 to 2, 4 to 1. Convert those energy gaps to wavelengths to get some more practice. So give that a try on your own. Feel free to email me if you have any other questions, and I will see you next week.
Thank you.
You're welcome.
Thank you.